Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right. Our next speaker is Yogesh Simhan, also from MSR West Coast. And he will be talking about performing science in the cloud, a haplotype phasing case study.
Right. So I'm also from the eScience group that David Hickam here heads. So a lot of things that Carl mentioned about the stuff that our group does holds for me too. And this is going to be, I'm going to be talking about work I did over summer and a little bit before with David and Girish from Indiana University, who was interning with us at Los Angeles. Girish already gave a talk this morning that sort of overlaps a little bit with this, and you see there are a bunch of other cloud computing talks today and tomorrow. So I'll try to tread carefully and give you something that's meaningful from this talk. So here goes. So the start of summer, we were looking, meaning I'm a computer science researcher, so I was looking at what's new out there, what's interesting to work on, and there was, is, and will continue to be a big hoopla about cloud computing. And given that a lot of work we do in our lab has to do with large-scale computation and data, this is something that we wanted to explore and see how useful it would be for the various applications we have in our group. The advantages of cloud computing are sort of well known, so you can scale out on demand, pay for what you use, and only use what you need. So you don't need to have a cluster sitting on your local group that you're not using. And it also allows you to essentially install whatever tools or software that you need. You don't have to go through some kind of sysadmin to get things deployed. You get a sandbox in which you execute, so you don't take down the entire cluster or something if you do something wrong. And you don't have to manage things too much. It's a bit of a pain and to manage a cluster with a bunch of users on it and have sysadmins to go and perform updates and make sure things are okay. So it also reduces the barrier to entry compared to other forms of, let's say, grid computing and high-performance computing. It's relatively easier, which is both an advantage and also a disadvantage if you want to do something too fancy. And as Carl mentioned, it's easy to stand up a service in the cloud and make it available to a broader community. You don't have issues with long-running services and having an open IP to your local cluster and so on. And lastly, in the spirit of Microsoft's dog fooding, we eat our own products. So it was also a good chance to try out Azure, which is being released in the Community Technology Preview. And also identify how useful Azure will be as a platform for science and see where the gaps are. So that either we could pass on the feedback to the product group or see if we can actually come up with some tools that would make it easier for other users in the product community to use science, to use Azure. So for those who are not familiar with Azure, I'll just give a brief overview. I know if you attended the tutorial yesterday on cloud computing, you probably know all of this. So Azure essentially gives you a compute node. It's sort of like a trimmed down Windows virtual machine, and it allows you to run it in different modes. One is a web role that's sort of, it could be a VM that's facing the intranet, so you can have a public endpoint, run your IIS server there and all your web forms and so on. And then you have worker roles, which are supposed to do the heavy lifting and all the computation and data processing and so on. And all of these run off a Windows 64-bit server, Windows 2008 64-bit virtual machine, and you have about 1.5 gigs of memory and 250 gigs local disk. And the access that you get is the equivalent of running applications in the user mode on your local Windows machine. And it also allows you to scale whatever application that you deploy between one or as many instances as you want automatically, yes, as the load increases. And also these VMs are transient, so you don't have control over when they start up and when they go down. So you can have a minimum number of instances running, but you don't get to pick which ones run. So that's a slightly different model for those who are familiar with EC2, where you stand up something and it's going to be running for a while. The data storage aspects, Azure provides 3 different storage models. Blob stores, which are like flat files. You can upload your file, and you can group it into containers, which sort of loosely map to directories. You identify a file by a unique ID. You can give it gets versions as you update the file. If you want to, you can actually treat the file as a block, as a set of blocks. So you can essentially do sort of random access with the blob store by fetching or writing a certain block. And a blob can be up to 50 gigs in size. So each file has an upper limit of 50 gigs, and you can have as many files as you want. Table store is sort of like a flat, it's like a single table. You can't have joins or anything, but it's just a collection of tuples, typed columns. And you can perform, it's only indexed by the key. You can perform queries on other columns, but the performance is going to be not as good as just doing a primary key lookup. And you can have up to 1 meg of data per tuple. And finally, you have queues, which are sort of standard queue data structure, except that they are durable. So you can actually, if you put something in the queue, you're guaranteed that it's going to be there till someone picks it up. And they also have a lifetime property, which allows a message to reappear if it's not been deleted after a while. And all of these are replicated 3 times, and they all have REST web service access to it. And finally, the SQL Azure is something that's sort of just coming out. The rest have been around for almost a year now. And that sort of gives you the full relational capabilities, but we won't go into that today. So this is just to give an overview of what I just mentioned. So you have the users out there on the public internet, and you have the user-facing sort of services and data providers right in the middle. So the web role, you can actually have your servlets and so on running. And queues, tables, and blobs also have a public endpoint. So you can essentially, from a desktop, you can fetch something or put something in the queue, ditto with tables and blobs. But the worker role, pretty much the only way to get to a worker role is through one of these. So you either talk to the web role and have it talk to the workers, or you go through one of the other data structures. So typically, in a typical model, the queue acts as the way to interface between the outside world and the worker. All right, so we sort of knew we had a platform we wanted to try. The next was finding an interesting application that would fit a cloud pattern. And we were looking at phasing of human genomes. So for those who are not familiar, the human genome essentially contains 2 different sequences, each coming from each of your parents. And these differ only at positions. And the statements I'm going to make is probably not going to be perfectly accurate for people who are familiar, who are in the biology field, but it's a sufficient enough approximation that you'll probably understand what I'm talking about. So the haplotypes are only different at the SNP positions, which are essentially the single nucleotide polymorphisms, where they are different at specific base pairs that are sort of well known, that have been well cataloged. And these SNPs appear probably 1 in every 1,000 base pairs. So 0.1% of the entire chromosome, and each of these haplotypes are going to be different from each other. And these SNPs usually have only 1 of 2 different values called alleles. And these SNPs are not uniformly distributed through the entire chromosome. So the goal of haplotyping or phasing is to actually identify these 2 different sequences that came from each of your parent. And that has some implications for things like looking at how diseases go from one generation to another. So whether it might probably be it might come from one parent more than the other. Or it's useful, there have been studies which show that haplotyping is useful for doing organ donor matching. much more accurate than general sequence matching. And also for things like drug response and so on. And especially given that the next generation sequencing technology, you've got all these machines pumping out genomics data out there. So the challenge is actually to go a step beyond just sequencing your data and actually go into more fine-grained haplotyping. Sort of to give you a graphic of what I'm talking about. So if you think of each of those two columns, two rows on the top, as the haplotype from each of your parent, and the colored boxes are the SNP positions. The grayed out boxes are sort of the rest of the other base pair positions. So let's say the first row is from the mom and second from the dad. Each of those positions, if they're purely biallelic, as in they're a complement of each, a perfect complement of each other, each of those colored boxes are going to have a different value. However, there are some sort of interesting differences which sort of make the problem a bit more complicated. For example, some of these SNPs could have the same value, in which, for example, the AA are the same and TT are the same. So they could come from, both parents could have the same. And you could essentially have some errors when you're doing some sequencing where the SNP values actually get exchanged. So what's actually supposed to be a G and a T is actually a T and a G, and so on. And finally, you could have potentially errors that are introduced that actually set the value to one of a non-SNP location, because each SNP can only have one of two base pair values of the four that are possible. So if for this particular, for the position over to the left, if A and the T are the expected SNP values and you find a C, that's not something that's valid. So these are essentially things that you need to control for as you're applying the phasing algorithm. So typically when you go and have your genome sequenced, so it's going to go through a sequencing machine, and that's essentially going to go and, as a loose approximation, snip up your entire sequence into smaller chunks. These are typically tens or hundreds of base pairs long. And then it sort of mixes them up, so you don't really know where what comes from. And here's where the computational stuff comes in. So this is one of the haplotypes, and this has been sequenced. The sequence read has gone through it once, and you get a bunch of these sequence reads. And the same thing happens for each of the parents' haplotypes. So you get a bunch of sequence reads from mom and from dad, and they all get mixed up because you don't really, right now you can't really sequence each of these haplotypes separately. And depending on the number of times you do the sequencing, typically you do it 10 or 20 times, so that you can actually reassemble them together. So you just get a bag of these sequence reads that have essentially chunked up each of those haplotypes about 10 times or so. And the goal here is to get back from this bag to the original two haplotypes that we started off with. In typical genome assembly, what you do is you start off with a reference genome. Let's say if you're doing a human sequencing, there have been enough human beings sequenced that you know approximately what the final genome is going to look like. So the problem sort of becomes taking this bag of sequence reads and aligning it against the reference sequence that you have. So the genome sequence between human beings are not all, between two different individuals are not all that very different. So resequencing essentially aligns all the reads together. And what you end up doing is you actually do something like an averaging across both these haplotypes. So when someone gets their human genome, it's actually something like an average between the two parents. So it might, for the SNP locations, you might actually get values from either of these parents, and you really don't know which of these it's from. So in typical genome sequencing, what you'll see is the bottom row. But what we would like to have is the top two rows from each of those parents. So there's a pretty interesting algorithm from UC San Diego called Hackert that's actually shown some decent performance in doing this phasing of haplotypes. This is from Bafna and Bansal. And it's actually a greedy graph cut algorithm. I'll just get to that in a minute. So the way it works is you treat each of these haplotypes as almost, since the SNPs can only have one of two values, SNP locations, you treat them almost like a binary digit. So if something is from one parent, you have a 0. If it's from the other parent, it's got a 1. And you go through and you start off with an approximate haplotype. Let's say this haplotype is from mom, and it has, let's say, all 1s. And you sort of assign arbitrary values to the sequence also, just making sure that it's sort of, you do a comparison against the initial haplotype you've selected, the binary digits, and you see whichever is consistent, and sort of do similar things to the sequence reads that you've got. And effectively, you take the initial haplotype along the sequence reads and convert that into a graph. And the way you do that is for every SNP position that you have, you map it to a certain node in the graph. And the edges between two nodes are going to be it's going to indicate the degree of dissimilarity between those two nodes, whether it's the sum of the reads that are consistent with the initial haplotypes and the sum of the sequence reads that are inconsistent with the initial haplotype. So that sort of gives you the degree of confidence that you have in those two particular SNPs being accurately represented in the first approximate haplotype that you've selected. So the higher the edge weight, the lower the confidence that those two particular SNPs actually occur in the same parent's haplotype. So this essentially means that if you go ahead and so there's an example. So if you treat all the X's as the different sequence reads and H as the two haplotypes from each parent. Here we are assuming they're purely biallelic because we do some pre-processing to remove the consistent ones. So if you'll see, each of those vertical columns are going to be each SNP position, and they map to one of the nodes in the graph. And if for two positions that appear in the same sequence read, if they are perfectly consistent with either of the haplotypes, you assign a negative weight, else you assign a positive weight. For example, if you took, let's say, 3 and 4, the third column and the fourth column, so you got a 1 and a 1 in the second fragment read, and that is perfectly consistent with the second haplotype. So you actually assign it a negative weight. If you take this third sequence read, you got a 0 and a 0, and that's perfectly consistent with the other haplotype. So you still give it a negative weight. Let's see, that's actually an easy one. So and similarly for the fifth one, it's a 0 and a 0, and that's still perfectly consistent. So you'll end up having a weight of 3 between 3 and a 4. Over there in the graph, the signs are actually inverted. So between nodes 3 and 4, you got a weight of 3, which is because 3 of these fragments are perfectly consistent with the haplotype. And the goal is, the key idea is that the fragments actually represent the truth, and the haplotypes are the initial approximation. And by doing multiple cuts of the graph, you're actually getting the haplotype to be more closer with what the fragments are. So effectively, the problem degenerates to doing a graph max cut and doing it repeatedly so that you edge closer to the final solution of the haplotype. All right. So in order to do this, what we did was use the Microsoft Biology Foundation, which used to be called Bio.net. And for those who have been around yesterday, there was a tutorial on that. So this is essentially a set of libraries that includes common parsers and formatters for biology, for files found in genomics. And it also gives you a .NET object model over common concepts in genomics. For example, you have sequences and you got SNPs and so on. And this actually makes it really easy to take any existing genomics algorithm and map it to programs, because you get a .NET object model and you get a built-in set of algorithms also that do a lot of simple stuff, so that you don't need to worry about. And meaning it's also been implemented in a pretty efficient way, so you can rest assured that there is an efficient library out there based on .NET that you can extend it and you can reuse it and so on. So it's perfect for defining APIs, for example. And again, the other reason to use it was, again, dog fooding. So this is something that was also being done over the past 6 months. And also find, in the same way, whether Microsoft Biology Foundation fits the need of, in this case, the phasing application, and if not, how can it be improved? So in our case, the input that the phasing was going to be getting was the assembled sequences. So that's phasing is sort of towards the end of the entire genome assembly pipeline. And the input was going to be a contig, which is essentially the consensus sequence, which is the average of the two parents, and the list of aligned sequences that's sort of been aligned by the previous stage in the assembly. The other data structure, sequences are the standard data structures for representing a set of base pairs. But since SNPs appear way less frequently, 1 in 1,000 base pair, we actually used a sparse sequence, which is optimized for sparse representation of base pairs. And there are also readers for reading in SNP data from file, so that you actually get an object model of the SNP reference database also. And the nice thing about MBF is that it's an open source tool, and it's actually getting a lot of, the idea is to get feedback from the community and have contribution from the community. So even during the few months that we were using, some of these, like contig, we were able to use right out of the box. Some of these, like sparse sequence, we were able to use it, but we had some performance issues, and we actually gave feedback to the team, and they were able to optimize it better based on our feedback. And some of these were actually tools that we ended up implementing and actually contributing back to the library. So some of the SNP reader stuff was built out of the work that we did with phasing. So, and again, this is opened up community, and I'd encourage all of you, if you're in this, try it. It makes it really, really easy. And I was someone who, probably a year back, I hadn't worked with biology tools at all, and it was quite simple for me to get started and implement this algorithm. All right, so broadly speaking, this is the workflow that we ran for doing the phasing. And the workflow is sort of quoted because it's designed to be compatible with the workflow system, and that all the various pieces of the phasing are modular. But we didn't really use a workflow system because we didn't have one that was compatible with Azure at that point in time. But the eventual idea is to have it compatible with something like Trident. That's also from MSR. So each of these boxes that you see are essentially methods, static methods in a library that are called from a single main method in a sequential fashion with some iterations thrown in over there. And it's mentioned the Hackert algorithm itself is more like a greedy algorithm that iterates and tends towards the solution. So you do a bunch of pre-processing steps right at the beginning to convert the sequence reads and the consensus to the bit format and map that to the actual graph. And finally, you iterate and run the max-cut algorithm and iterate to find the eventual solution. And in the way we designed it, the workflow itself was running on a local laptop and or desktop. But each of these steps that you see over here was running inside Azure within a worker role. and essentially the interaction between the local machine and Azure was by passing the values either by reference or by value, depending on how they were. And I'm just going to summarize the experience that we had with Azure, because I think that's one of the more interesting takeaway messages. The rest was actually to find out what these pros and cons was. So one of the nice things that we found about Azure was it was pretty trivial to parallelize the particular algorithm we had. Like Carl mentioned, it was, what do you use, elegantly parallel? Delightfully parallel. So the phasing algorithm was delightfully parallel across chromosomes. So we could essentially run each of the 22 chromosomes that needed to be phased in parallel, and we could do that pretty trivially without actually having to code any of the logic in our code. Azure is also well suited for pipeline applications. So if you've got a task that finishes and passes something off to the next task and goes in that particular fashion, it's pretty simple to actually take that workflow pipeline and push it into Azure and have it work. And we had literally, we didn't have to make pretty much any change to our code. There's a caveat on that in files, and I'll sort of come to that in the next slide. But it was pretty much taking it, opening it in our Visual Studio, implementing the couple of roles that we needed, and pretty much right-clicking and doing publish, and it's pretty much going to run in Azure. And you can do that for any .NET project or Win64 binary if you had that. Plus, you get all the other advantages of cloud computing that I talked about right at the beginning. So the negatives, which are probably more interesting. So we were working, this was during the summer of this year, and we were still working with the community technology preview. So this was the beta version that's pretty much available to all of you right now. And some of these negatives are probably due to that, but some of them are more intrinsic to Azure. The fact that right now, the way a role is designed, a worker role is designed, you essentially have to write a bunch of template wrapper code for every sort of unique application that you want to write. So in a sense, there's still the barrier to entry is still a little bit more than what it should be, I think. So you can probably write a hello world program starting from scratch without knowing anything about Azure, probably in 30 minutes time. It would be nice if you can do it in 5 minutes. And also if you wanted to pass parameters, you have to go through the queue and so on. So some of the work that we did and Girish talked about this morning was to actually see if you can build workers into which you can pretty much inject any code that you want and have it run. So if you had a local executable or just a method in a DLL that you wanted to call, you don't actually have to go through opening up Visual Studio, creating a role, and so on. Just have a simple utility that will transparently get injected into a worker role, and you just call it using a simple interface that we provide. The other issue we had, which actually forced us to stop our measurements of the various, or stop phasing of various chromosomes, was to do with I/O performance. So from rough numbers that we took, for interfacing with the blob store that you have in the backend within the cloud and the actual worker role VM, the read and write performance that you were getting were around 10 megabytes per second read and 1 megabyte per second write. And that sort of works for small data files, but once you start getting into big, huge data-intensive applications, that might start being a problem. And an advantage for us with phasing was that since we were only dealing with SNP data, it was 1,000th the size of the typical genome data that you would find. So it sort of worked out okay for us. But we have some initial ideas and implementations of how we can sort of do some intelligent caching of the data. For example, the SNP reference file that we had to keep downloading it for every worker role. And that's something that caching might improve. But there's also work going on in Azure to actually do some intelligent file movement and replication so that Azure does that for you transparently. And hopefully down the pipe, you won't need to do anything on your client side. And finally, partly because it was beta code, the ability to log and monitor your worker role, sort of debug stuff in the cloud, was quite challenging. Azure does provide you with a desktop version of Azure, which is useful for initial debugging. But once you got 20 or 30 roles running within Azure, the current logging framework that they have is pretty simple and not really intended for distributed logging. It is going to improve soon, so I don't think it's really going to be a long-term problem. But essentially, with some help from the Cloud Computing Future Group, which is another group in MSR, we got some initial loggers and so on going. Some of the sort of surprises that we found was a little bit due to the 64-bit architecture that Azure has. And we found that things that we could run on our local laptop that had about 3 gigs of memory and 32-bit architecture wouldn't run in Azure because there was something like a 50% overhead because of 64-bit pointers. So for those who are sort of used to working on 32-bit and going to 64-bit, I mean, those who are already done, they might already know. But this was actually one of the sort of surprises that we had. And the initial version of Azure that you have right now only has 1.5 gigs of memory. So if you've got high memory requirement applications, it's probably not going to work right now, but soon enough they're going to have multiple flavors of the VMs. Handling lots of small files is just not scalable because there's almost like a fixed cost, fixed overhead per file of a couple of seconds for doing read or write. So if you've got thousands of them, even though they're extremely small, that's going to really chew up time when you're going between the blob store and your local store. And one thing that's sort of interesting is that some of the CTP version, the beta version, has actually improved over the course of summer. So things have sort of becoming quicker. There are more utilities out there, and so on. So that's a good sign. So to conclude, there are a suite of tools that we've used inside our group, many of them from other groups within Microsoft, like the Microsoft Biology Foundation, the Trident Workflow, and Azure. And Azure seems to be a fairly feasible platform for science. And one of the nice things is that there are a lot of tools that are starting to emerge, both from within MSR and the products team, and also from various other academic partners that we are working with. And meaning CodePlex has a bunch of tools that have been developed over the past few months that actually plug in a lot of these various different gaps. So there's a thriving community out there, partly because Azure is also targeted towards the business community. So you got a lot of other open source stuff out there. And a plug for Microsoft Biology Initiative that's really helped us shorten the time to science, at least in our particular case. So thank you.